Hello, my name is LXAI, and today I'll be talking about a research that I've been doing together with Felipe Polo. We are developing a method called OCDE, Odds Conditional Density Estimator. It is very common in many statistical applications to do inference of an interest variable y conditional on a vector of non-covariates x. Regression methods summarize the relationship between y and x through the expectation of y given x. More generally, we can have this relationship summarized with conditional quantiles using quantile regression methods. These quantiles are very informative if you have well-behaved distributions, like a Gaussian distribution. However, for distributions that aren't well-behaved, for example, that show multimodality, asymmetry, or heavy tails, regression methods can be misleading. In these cases, conditional density estimation can be a better approach to do inference. In this research, we propose a CDE method, which we refer to as OCDE, Odds Conditional Density Estimator. Suppose that we have a dataset D of size n, where y is the variable of interest and x are covariates. The objective of the CDE problem is to estimate the full uncertainty of y given x, that is, the full conditional distribution of p of y given x. Our method consists in introducing a so-called instrumental or artificial random variable, y tilde, which we will choose to have a known distribution. It is important to choose y tilde so that its support contains the support of y. The key idea for the OCDE method is to notice that p of y given x can be rewritten as the product of the density of the instrumental variable, p tilde, and a density ratio, the joint density of y xy over the joint density of xy tilde. As py tilde is known, we are left with estimating the density ratio. We will estimate this density ratio with the probabilistic classification method. This way, the problem of estimating the density ratio that is non-supervised becomes in practice a classification problem, which is supervised and easier to solve. So let us create another instrumental distribution S of Bernoulli 0.5 and define the random vector x prime y prime such that the p of x prime y prime given s equals 1 is the original joint distribution of xy, and p of x prime y prime given x equals 0 is a joint distribution of x y tilde, which are independent between themselves, as y tilde is generated independently for xy. By the Bayes rule, we can write the conditional distribution of p of y given x as the product of py tilde by this rewritten form of the density ratio, for which we just need to train a probabilistic classification method to estimate. In order to grasp the potential of our algorithm, we provide now a toy experiment where our xy variables have kind of a circular joint distribution. This way, the distribution of x, y given x is multimodal in almost every point of the x domain. And this example is particularly useful because we can clearly see that the expectation of y given x induces a point that has no probability mass, and thus regression methods would be misleading in estimating the relationship between y and x. For our instrumental distribution, we sample y tilde from a uniform distribution and we plot the points from xy in dark blue and xy tilde in light blue. Finally, we train a cat-boost probabilistic classifier to learn to distinguish between the points that are sampled from the original data, previously in dark blue, and the instrumental data in light blue, using the x and y as covariates. The figure below shows the distribution estimated with our method for varying values of x. For values of x between -5 and 5, we have the symmetric multimodal distributions as expected, and for the only values that induce a unimodal conditional distribution, that are x equals 5 and -5, we also observe this result with our method. For real data, we tested OCDE against two other known state-of-the-art algorithms, and OCDE displayed a competitive performance against both when evaluated by the CDE loss. Also, we will make our preprint and Python package available ASAP. Please contact us if you'd like to receive it. Thanks for watching.